believe we're doing dynamic programming today.
Yes.
Okay, cool. And you've done all the, or you've done I'm assuming you've done a few problems that IK has provided.
Yes,
Can
I
you tell
have.
me how that's been for you?
It's been challenging. Dynamic programming is probably one of the more challenging topics I've done.
Uh,
Yeah.
what sorts of problems did you find were more challenging than the others?
Just a general way of thinking because it's an optimization problem and thinking what kind of data or I should build, what kind of array or 2D array to build in order to contain that data, so I can use a decrease and conquer method to find the previous results that I need to action upon or to analyze from my current result. That's been a little challenging, just to figure out like what kind of data I need to store.
Okay. We could cut and do a brief debrief on how we can improve on dynamic programming.
Sure. Yeah.
Okay, cool. I see that you're already on the CodeBunk. Can you go ahead and share your screen of the CodeBunk editor?
Okay. Can you see it?
All right. Yep, I can see your screen. Okay, so I'm gonna go ahead and write in the comments section a couple of, or I'm going to paste in a diagram and I'm going to talk about it.
Okay.
But before that, could you go ahead and hit the run button at the top left to see if the code can execute? Cool. All right, then I'll paste it here so we can avoid that from happening again. And I'm going to put in, so have you played an RPG, like an old school RPG?
Yeah, like Final Fantasy.
Okay, cool. Then this will help a little bit. So essentially, I have, I can interpret this matrix as a game board. And I want to travel from the top left corner to the bottom right corner.
Yes.
And you can see that, I have numbers within each cell of our matrix. Each cell is kind of like a level.
Okay.
And in each cell, the number here pertains to the amount of damage I receive. So in the first cell, right, I fight this boss, I lose 2 health. Then if I go to the right, I lose 3 health.
Right.
And then when I move to the right again, I gain 3 health.
Okay.
Essentially, I start off this entire map with a set amount of health points. And then at each cell, my health points get subtracted by whatever is in each cell. So if my health points go down below 1, so once it hits 0, it's game over for me.
Okay.
So now I want to know, what is the minimum amount of health for me to start at the top left corner and travel to the bottom right corner, so that my health will not ever go down below 0 or down below 1.
Okay. And is there a starting health?
That's what we want. So in this case, our output here, our output here is 7.
I see.
Why is it 7? Let's suppose that we already have our most optimal path given to us. And I'll just let you know right now, we first go this way to -33, and then we go down.
Right. So that is total. Okay, I see.
Our total change is 7 minus 2 minus 3 plus 3 plus 1 minus 5.
Okay.
So by the end of this, we end up with 6. We end up with 1. but we take 6 damage.
Okay. But you would have to, and it's in order too, right? You can't like take all negative damage and then have all the positive damage.
Right.
So all the positive increases.
Right. So the minute our health goes down, it's game over for us. So we can't start a specific level with an HP that's below 1.
Okay. I see. Got it. 6 and 1. Got it. Okay.
So here I'll paste in the path. And this is our only input. It's just the board.
Got it.
Okay. Do you have any other questions?
How big or small the board can be?
That's a great question. So let's say that we can have, so let's say we had a R and C as our rows and columns.
Right.
Our rows and columns will be less than 200 and greater than or equal to 1.
Okay. And what about the values inside? How big or small the values?
Another great question. Let's say that we'll have those values bounded. So I'm going to say dungeon of R and C will be no greater than 1,000 and no less than negative 1,000.
Okay. And it could be any size, any size matrix as well. Oh, actually, yeah, it could be any size matrix, I guess. Okay.
Any other questions?
Are there more than, if there's more than one path, do you want to return the smallest output?
Yes. So in this case, we always want to return the minimal starting health.
Minimal starting health. Okay.
Right. There's multiple ways we can go about this, and if we start off with like 1,000 health,
right,
we can take any of these really easily.
Right.
But we're bounded by the starting health we want to do. So we really want to optimize and speed run this game so that we can go to the bottom right with the least amount of health.
And if there is no path to the bottom right, what are you trying?
Great question. So in this case, we can always have a path.
Okay. Okay. Let me think about this one. I mean, I think the general algorithm is to use a decrease and conquer method, and starting from the lower right, as the bottom right, where we're going to choose either. I'm sorry. One more question. The path can only be left or down, right? Or the navigation could be any other way.
Let's say we don't have any bounds in which way we can go. I will say that for us to go from one room to the next, we have to go to a cell that's directly adjacent.
Directly adjacent. Okay.
So to the left, to the right, we can't hop.
And you can't do diagonal.
And we can't do diagonals. Yes.
Okay. Okay. So for the bottom right, the -5, the destination, there's only, you can come from above it or to the left of it, right? To cell above it or cell to the left of it. What I'm thinking is for those cells, what we need is to find out is what is the number, what is the health, I guess, once you hit those cells. So if you hit the 1 and the third is the health and the 30, what is the number that you have? For instance, here, let me do this. I'm going to copy of this thing. For instance, I'll do this. So if we hit, so to make it through to -5, to make it through, you would need these cells to be greater than -5, right? But then you would just take, at this point, I don't know what those numbers are, but let's say it's greater than -5. And then I would take the smallest, the minimum of those two numbers. And that is the path I would take to get to that destination of -5. Sorry, not -5, +5, so greater than +5. So you would be 6 or greater, basically. So in this case, if it's -5, I would take, I would just need to be a 6. And that this actually is going to be a 6. And then this is going to be, I don't know what that number is going to be, but that could be a number. This is 6. And if I work backwards, I'm like, okay, to get to 6, and to 1, I would need to be I would store a 6 here, and I'll store whatever other number here, and I would take the minimum of those, and I would take that 6, and I'll be like, okay, 6 minus 5, I can still pass, I can still get this point by taking the minimum. So I would say, so if I did a recurrence equation, f of n will be the min of it will be f of r and c equals the min of f of r minus 1 and c and f of r c minus 1. The minimum of those two, but also needs to satisfy that once you that is greater than -5. So okay, I shall write that. F of R C. No, sorry. So let's call it dungeon R C. So I can do this. If I did that, so I would choose the minimum of these two. This 30 would be, let's say, I went to another path, and it came out to be like, let's say this is the path, and This came out to be like 35 or something, like 40. No, this will be 40 minus 10 minus 12, 30, 22, 28. This will be like 28. So it's between either choosing 6 or 28. I would choose 6 in this case. Yeah, actually, I don't need this. I don't need this one actually. Good. I will want to check, and I will want to check if dungeon RC is greater, sorry, if the numbers are positive. I'm gonna have to check if the numbers are all positive or not. Actually, dungeon, it could be any positive, negative number actually here too. So I would have to do that. Greater than 0, and greater than 0. So I would check if the neighbors, to the top and to the left of it, is going to be, if you add the cell, is going to be greater than 0. If it's negative, then you don't take that path. But if it's both are positive, then you take the minimum of them. Okay. Now the base case, to get to a starting point of this, is going to be, so f of 0, 0 is going to be dungeon 0, 0 plus 1. I think that's a base case. So whatever, is that true? That could be a positive number as well. Okay, so if it's, I guess it's, if dungeon is negative number, then it's plus 1. If it's positive, then it's just 0, 0. So if negative, and this positive, then it's just that. I think that's my base case. So then if I work backwards, I could be like, okay, this is 6. Okay, now from 6, sorry, this is, yeah, this is 6, this is fine. From 1, which one do I take? 1 plus 1 plus 4. Let me think about that one. The minimum of these and plus R and C will give you this score. Okay, so f of 1, 2, 3 and 2 and 2 is equal to the min of those two scores is 6 and 28. Plus -5, which is equal to 1. Okay. So the answer just would be 1. Oh, I see. My problem is now I got this, but I have lost how much the starting health should be. Hmm. Hmm. Actually, I could store just the minimum of those two numbers in here. Store the minimum number. I can say what's the minimum here. And store 6 in here for this corner here. Okay, so I would say for -5, -5.
Can I ask you a couple questions?
Yes.
So how did you get 6 and 28 for the cells 2, 1, and 1, 2?
Um, I think I did that by I think I did that by 28. I'm not sure about yet, but for this one on top, I took this cell and added it to that number in that cell
Okay.
to get 6. So I took basically I know I'm going to decrease by 5. I added a number. So I took the inverse of this number and then added to this one.
By inverse, you mean the negative
the
if it's
negative,
positive.
yeah, the negative of that number.
Okay.
Added to here.
Okay.
So that I know for that cell above, I need at least 6, right? I think maybe it's not 6, maybe it's like 7 in this case. Like I need at least a 7 to come to pass this cell and then have a 1 at the end after you're done.
Okay. Let me go through a suboptimal path with you. So in this case, I'm looking on the grid between lines 27 and 29.
Mhm.
If we go from -2 down twice
Mhm.
and then to the right twice,
Mhm.
the minimal amount I need here is actually just 8, but
Mhm.
yeah, it's still minimal. So if I do this, 8 minus 2 minus 5 plus 10 plus 30
Mhm.
minus 5. My value won't necessarily be equal to 1 though. So
Mhm.
so I get your approach here, but supposing that all the values surrounding this was an insanely high number,
Right.
are we still able to think of the equation this way?
Because I was assuming that we will get to 1, just barely made it, but that doesn't mean there's a path to get to 1.
Mm-hmm. Right. 1 is a value we should aim for, but it's not necessarily the value we end up with.
Right.
So let me also just point us in a, I'll just do this. 1 minus that.
One minus that. You're taking the 1 from 2, 1, and you're minusing the rest of it. -2, -3, 3. No, you have the 1. -2, -3. -2, -3, 3, 1, and 5. -5. Oh. So that would be 0. Use all these numbers, add up to 1. Right, so you have 7 equals 0.
So this is -5 plus 3, -2 plus 1, -1 minus 5, -6. So this would just be
Oh, I see.
7 minus 1 minus -6.
So this 1 is, or you just took the 1 and put it, or you took the 1 and you moved the 7, you moved everything else over to the other side, or the right side of the equation. Except
Right.
for 7, but you moved everything else. I see. So you're looking for a path that takes the inverse of the number, the negative of each number, and adding it up.
Mhm.
Let me think about that one. For the negative of this, so you took so this would be a +2, +3, -3, -1, and +5. That would, if you worked, backwards, you would go 5, -4, 1, 4, and 6. You get to here and you have 6. And if you add 1 to 6, then you're good. No. All right. So this would be, so okay, so if you work backwards, you come here and you come to 0, 0, and you have 6. That's the minimum amount you need to survive this path to get to 0. So you add 1 to that path, one to a number. So let's see. Just to get here, you need 5. To get to here, you would need 4. To get here, you need 1. To get to here, you would need 4, and again, you need 6. And if you add 6, that will work. So if I did it for the other direction, if I did 30 here to get to here, so if this was a negative, I would need so this would be negative 30, 10, 5, because that was a 2. So to here, and to get to here, I would need 35, 45,
Why would you need 45?
oh, no, I just need to add, so I need to add these up. 25.
We're doing the 2 downs and 2 rights, right, in this case?
2 downs and 2 rights, yes.
Okay.
Negative
Our
15.
minimum value should just be 8.
Okay.
But even then, it's still greater than our actual minimum value, which is 7.
Right. So then this negative 15 minus plus 5 would be
You're
-10.
very, very, very close right now.
And then this will be negative 2, negative 8. Either 6 or negative 8. Then we just take the minimum here in that case. I think I did something wrong here, but this 5. So inverse these, take the negative all these numbers. Just decide which path to take. Five minus. Wait, why did I did this was 5 minus 4 is equal to 1. 5 minus 1 equals to 4. Okay. And so I did here is 5. Sorry, here 5 plus negative 1 is equal to 4. 5 plus negative 30 and negative 25. Yeah, that's the way. Negative 15. And negative 25 plus negative. Okay, now I guess I'm trying to figure out how to choose the path then. I guess as soon as I get here, I would just take the minimum of that. So for each one, I would take the minimum of that number. So here's 4 and here's negative 10. I mean, I guess this probably should be 10, but So for here, for cell 00, so it looks like we need to look at cell 00 then, instead of the bottom right. Look at the cell 00. Determine at this starting point what is the health that's needed. Now we'll look at if these were, let's say, these were this. I would look at this path or this path. That's a positive number. Then I can take that path. So I did 2, 2. I did 2, 2. I would take the inverse of that number, or the negative of that number, and work backwards. Work backwards. 4, 1, 4, 6, 5, 25, 10, 8. Five. There could be multiple answers that get to 6. I get to 0, 0. You take the minimum of all those ones. For let me try something here. Okay. To 5. Before. Yeah, that's because I know the path. That's why I know how to traverse it that way. But if I didn't know the path, which path to take, F4 would be the.
Can I give you another hint?
Okay.
This might be the one that gives it away. Are you still okay with that?
Yes.
Okay. Coming right up. I will be on line 45 here. So this is a chart that is dependent on the examples on line 7. Actually, it might be better if I put them closer together. But why don't you read it out loud, or internally, and tell me what the numbers represent.
7, 5, 2, infinite. 7, 6, 1, infinite, none. 1. I mean, the starting 0, 0 is the smallest health for a successful path that's needed to get to the right corner of a dungeon, the lower right corner of a dungeon. This would be a DP table. This would be a DP table with, that's expanded by ones, one row, one column.
Mm-hmm.
7, 5, 2, 5, 6, 1. So 2, 2 is 6. You would need a 6 to become a 1, and 3, 3, 2, and 2, 3. Hmm. 7, 5, 2. So you would go 6. You start off as 1. Okay, so you start at 1. I think you start at 1 as the minimum, and you try to go backwards to 0, 0. And you add you add the inverse of the negative of that cell as you go backwards.
So in this case, could you tell me how we got 6?
So it'll be
Given that.
1. If you initiated this DB table and you initiate these two ones, 2, 3 as 1, so it's 1 plus negative 5. Sorry, 1 plus 5. You get 6.
And if we had something that was like this, negative 5, then with just these two, like this 2 by 2, this could work, right? For this. We could just have this and this.
1 and yeah.
Right.
Yeah.
That would be the table for this.
Oh, yep, yep.
Right, these. So what if it was like this?
If it was like this, then it would be 1. So the 6 will be a negative 5 then.
Okay, so we can start with negative 5.
Mm-hmm.
Let's say that, we can't do that, because if we can start with negative 5, that means that the RPG character starts with negative health and immediately dies before the first turn.
Right. So we can start with maybe a 1.
1.
Yeah.
Right, it would be a 1. So our condition here is to take there are a couple things here. If the value is negative, we have to take the minimum of the two values, one here, one here, and add or subtract, because we want the minimum value, the health, or the amount of damage you take from that cell.
Right.
And then compare that with 1.
Yeah. If it's,
so in this
you
case,
take the maximum, like it's 1 or that number, right?
yeah, we would take the maximum of 1 or the number we get from subtracting the damage we would take plus the values to either our left or our right.
Yeah. Yep, and then for this one, and for 5, you would take this one infinite and you take a 6. Take 6 and for 5, what would you do? For 5, you would take this. You would take the minimum. Oh yeah, you would take 5. So the 6 will be. You would take 6 minus 1, which is 5, or you take infinite, but infinite is bigger, so you take the minimum of that one. So that's 5. And then 2, you would take 5 minus 3, or the infinite, and you take 2. And 2, and then 5, you would take. Now you can compare it with. Yeah, now you can compare it with 2 plus 3, or you can take 11 plus 3, and you take the minimum of that one, and you take 2, and you take 5 here.
Okay.
Okay, take 7 would be 5 plus 2 is 7, or you take 6 plus 5, which is 11. You take the minimum of that, which is 7. 6 plus 5, yeah, it's 11.
We take the minimum of that and then compare that with.
You take the minimum of that. You compare it with this, the above, to left, to right of it, or to the below it.
Mm-hmm.
You take the
But
minimum.
what if both of them were extremely positive?
Both of them extremely positive, and you just take the minimum of those values.
So let's say, right, instead of -5, I had
Mm-hmm.
a 100, and then here I
Mhm.
also had 100.
Mm-hmm.
Then instead of doing, in this case, for 7, we got 5 plus or minus -2.
Mm-hmm.
It would be like -2
Oh, I see.
or yeah, 5 or 100 minus or whatever arbitrarily large value minus -2. But we don't need that, right?
Yeah.
Because if they have that big of a number such that we're coasting, we need to compare that with another value so that we don't need to have more than we need when we go into our dungeon.
I guess you compare it against 1.
Yep.
Yeah. So you're not using too much. I guess having too much help.
Yep. And that's how it works.
Okay. Yeah, this one is was pretty challenging. Just to wrap my head around like the DP table, I think that was the hard part.
Oh yeah, initializing your DP table is the trickiest part of DP. Just as a quick tip,
yeah,
this is how we would initialize our DP. We would have to start from here, which is 0122, which is the size right here, and then update our values as we go back up. So the way our DP table would iterate is this value, then this value, then this value, this value, this value, this value, this value, this value, and this value. So this is a variation of DP called bottom up. Not bottoms up, bottom up DP.
Yeah.
And it's called that because we start from the bottom, work our way up, and build our values as we do it.
I see. So in this case, you're not picking a particular path. You're just updating all the values, and the minimum path will kind of show up.
Exactly. And the only reason why we can do that is because of the way we initialized our values here. No value is greater than infinity. So when we do our first value, we're always going to not end up with infinity here. So it's a very, that would be a sort of like our base case. That's why I wanted us to do this one. If we start out with float infinity, then we would be comparing the minimum between 1 and infinity. So that would have been, that would have taken care of that use case.
So how would you have like come up with the DP table?
Right. So here are some tips on DP. In the beginning, I feel like the hardest part was walking through this problem, this 3x3 grid with many cells. I would say first start off with a smaller version. So make your own input, like what I did on line 12, right? We already have the bounds that our rows and columns will be greater than or equal to 1. So we start off with this. Then we think, how are we going to, what do we output here, right? We wouldn't in this case, we would output 6, and then think about different cases with small outputs. So what if our value was positive? What would we output here? Be 1. So now that you have your small cases considered, you don't need to worry about coming back to this problem again. This would just be taking the maximum of the values minus your current value, or 1. So that's already a huge part of what you have to do. Then you start expanding outwards. Like, what if I add an additional row? Then what would it look like? What do I have to do here? So usually the first example they give you isn't always the best example. Start with a smaller example, work your way up. In this case, since you know you have an array, a 2D matrix, and you know it's DP, chances are it's going to be bottom up, not top down. So with a little bit of practice, you'll start to like see a pattern of what type of DP to use. Well, I can just tell you always, when you have a 2D matrix, bottom up's typically the way you should go. And then when you have like a straight array, then it would just be like the one you have on one of your tabs, the jump game. It would just be like that. In essence, every DP problem is a flavor of a different DP problem that you may have seen before in the past. Don't think about solving the problem straight up. Think about how this relates to a DP problem you've seen in the past, and then that would be the best case for when you do DP problems.
Okay, so for like if it was like a 1D array, like Jumpman, you would go, you would increment from like small to big, right?
That would be a little different. So in that case, you have 2 choices here. You either, or sometimes 2, sometimes 3. You either jump once or you jump twice.
Right.
And so then instead of doing the up one row, left one column, you would do -2, -1 of your index. So
Right.
it's a little different, but more or less you get it's the same gist.
Got it. You always start from, so yeah, you're populating a DP table from the bottom and going up. So from you populating from the destination and saying, okay, now from this destination, how do I get to this one from my neighbors?
And when you're making comparisons, start off your DP table with your row +1, column +1, and then decide whether or not it's plus infinity or minus infinity or 1 or 0 or none. Typically, you won't need the bottom right part of your DP, so you can use none there. But it's going to be very, very useful if you make a table like this.
Okay.
And then you think about ways to populate it. And then you don't even have to start with something like this, right? And make it a 2x2, have float, have some value at the top left, and then have none on the bottom right, and then think about it that way.
Okay. When you think about if it's like you're saying, if it's positive infinity or negative infinity, just so you can bound it.
Right.
Okay.
And then always just think about like what, and just substitute that with whatever values you have in your input.
Got it.
Okay. Real quick, just as a sanity check, and so that I can write it down in the debrief. Can you give me in order of row and column, what's the space and time complexity of doing DP?
It would be, so for time complexity, since you populate every single cell, it'll be the length of the row time, the oblique of length of row times length of column.
Cool.
And then space would be the same thing because you have a DP table of that size.
Yep.
Even though you have one extra row, one extra column, it doesn't matter.
Yep. Exactly. No tricks, no gotchas there. Just want to write it down that you thoroughly grasp space and time complexity. Cool. Do you have any questions for me? Do you have any sort of comments on this question in general or dynamic programming?
How would you go about, like you're saying, I loved how you said, there's these kind of patterns to adhere to and kind of populate. How would you think about, if you have this DP table, what values to put into this DP table?
What values to put into your DP table? Great question. It differs per problem. So this is a LeetCode hard. The reason why it's hard is because the values you put in here are slightly different. So a 1 is, you rarely see that in the DP table. Typically it's like 0, infinity, or negative infinity. That all depends on your problem. I would say if you do more practice and you write out the table here as an exercise, then you'd be able to get to know get familiar with what you should initialize your table with. Okay,
got it. So just you're saying just start with like a smaller example, and give that DP table going and see how you build that example bigger and bigger.
Right, and then for the practice problems you do, write out what it starts with, what your DP table starts with, write out what your DP table ends with. And then over time, with enough practice, it'll be like second nature. Okay. Well, that's part of what the solutions in the discussions don't show you, because it's time consuming to have to write all that out. But a couple of you do this 5 times, and I swear you'll become twice as better at dynamic programming than even me. So, so yeah, that's about it. I have to go. But it was nice talking to you, and I think you have it really down. I wouldn't stress too much about dynamic programming if I were you.
Okay.
Best of luck on everything, and
Yeah, thanks. Bye.
enjoy the rest of your weekend.